Okay, this is Chapter 12, Chemical Kinetics. This lesson for the first half of this, which will cover Introduction to Reaction Rates, rate laws, the types of rate laws, method of initial rates, and integrated rate law. This lesson is fairly long, so I'm going to break it up into several components. But you will need to watch all of the components in order to understand the first half of the problem set. I suggest that you have your calculator out and that you pause and replay as needed. This is not an easy topic, and you may also have to refer to the book and read through the different sections to reinforce what I'm going to be telling you now. I've supplemented your note packet with some PowerPoint slides. The PowerPoint slides aren't really necessary to write down unless there's something specific that you want to gain from it. It just reinforces what I'm saying at the end of each section. So, what do we mean by kinetics? Kinetics is the study of the speed at which reactants are turned into products. These are called reaction rates. So we're going to be studying reaction rates. Spontaneous reactions are reactions that will happen, but we can't tell how fast. For example, diamond will spontaneously turn into graphite eventually. A reaction mechanism, which this lesson does not talk about today, focuses on the steps by which a reaction takes place. So for example, when we look at a reaction, we only see the reaction. We don't see the little mini reactions that are taking place behind the scenes. So when we look at reaction mechanisms, we're going to look at those smaller steps. A reaction rate is really a change in concentration at two different points divided by the change in time. Please remember that whenever you see these square brackets right here, that's referring to concentration. So anytime I put something in square brackets, it's the concentration of that species. So let's just first, and we're going to get to this in your notes, but I just want you to listen right now. We're going to look at this reaction between diatomic nitrogen and diatomic hydrogen to produce ammonia. As the reaction progresses or proceeds, the concentration of H2 is going to go down. That makes sense. It's being used up. The concentration of N2 is going to go down 1/3 as fast. Well, how do we know this? If we take a look at the balanced reaction, we can see that you need 3 times as much hydrogen to combine with nitrogen to form the ammonia. So the hydrogen is going to get used up a lot faster than the nitrogen. And as the reaction proceeds, the concentration of NH3 will go up. So, in your note packet, the rate of a reaction is measured with units. So the rate refers to the time, and that we know that solution is molarity. So the rate of a reaction is going to be measured in moles per liter dot seconds. It sometimes can be measured in minutes. You'll have to look at the data table that you're given. So we're really monitoring the change in moles over the change in time. Often students wonder what chemical is the rate determined by. Which one do I know to use? Well, honestly, it's the easiest chemical to measure, depending on the reaction. And you'll see as we go through a couple of these examples, it's not too hard to determine. So in your note packet, you're given the example of nitrogen dioxide yielding nitrogen monoxide and oxygen gas. Let's just determine what happens first in this reaction in words before we try to graph it to see what's really going on. So when we look at this, we can see that the rate of consumption of NO2 is equal to the rate of production of NO, which is equal to 2 times the rate of production of O2. So if I were to put this in an equation, I could say that the change in the concentration of NO2 over the change in time is equal to the change in the concentration of NO over the change in time, which is equal to 2 times the change in the concentration of O2 over the change in time. So that's just kind of setting up a basic synopsis of what's going on when we look at this equation. And we can see that by looking at the moles of each of the species in the reaction. Now, if we were to actually use, and you have this in your notebook, the concentrations of the reactants and the products as a function of time, we can kind of graph this. So if I look at, let's plot all 3 lines. Let's start with NO2. We know that at time 0 that the concentration of NO2 is 0.01, which is way up here. And we also know that at time 400 that the concentration of NO2 is 0.0031. Well, this is 0.0025 and this is 0.05. So I'd say it's probably going to be somewhere around in here. So if I were to draw a line of that, I'd get something like this. Okay, so this is my NO2. Now let's graph my NO. My NO at time 0, my concentration is 0 because nothing's happened yet. And at time equals 400, my concentration is 0.0069. Here's 0.005, 0.0075, so it's somewhere, I'd say up here. So I draw a line for that. And this is my NO. And my third line is for O2. Again, it starts at time 0. It has a concentration of 0. And it winds up with a concentration of 0.0035, which is slightly higher than the 0.0031 where the other one ended. So perhaps it's like this. Oops, that was a little overshot. O2. But you kind of get the drift. Now, we haven't even really done any math. We've just looked at some data, we've looked at an equation, and we've made some predictions. But we need to be able to solve this all mathematically. So let's break it down. Okay. When it comes to rate laws, we have 2 different types. The first type that we have is called a differential rate law. Which from this point forward is really just called a rate law. So whenever we see rate law, we're really talking about a differential rate law. And what do we know about a rate law? It expresses how the rate of a reaction depends on concentration. So this expresses how the rate of a reaction depends upon the concentration of the species. And there I put the brackets so you know whatever that species is. And then we have an integrated rate law. which is also, sorry, and this is, we have an integrated rate law. And this is how the concentration of the species meaning the reactant or the product depends on time. So those are the two different rate laws. Now, we talk about a differential rate law. The form of the equation is as such. Rate equals K times the concentration of A raised to the X times the concentration of B raised to the Y, where K is the rate constant, or what's sometimes called the proportionality constant. It's found only by experiment. The values of X and Y determine the order of the reaction. So the values of X and Y determine the order of the reaction. X and Y will be an integer. It could include 0 or it could include a fraction. When we determine the order of the rate law, we're going to look to those values of X and Y, and it is the sum of X and Y exponents. Right now we're just getting our feet wet with terminology. So in this example, if the rate is equal to the rate constant times the concentration of A, then this is a first order reaction. Here, my rate is equal to the rate constant times the concentration of A squared. This is second order. Here I have 1 plus 1. This is second order. And in the last one I have 1 plus 2, so this would be third order. Okay, let's look at this example over here which you don't have in your book. Here's another way to look at things. Determining the value of N, or the order of the reactant. So N here is equal to my X and Y in my previous examples. It depends on how it's presented. Sometimes it's N if they're talking about one thing, X and Y, Z if it's more than one species. If I look at what's going on between the relationship of the concentration and the rate here, I can see as the concentration is doubled from 0.5 to 1 that the rate quadruples. So if my concentration doubles and my rate quadruples, then this would be second order. So my rate formula would be rate equals the rate constant times the concentration of A to the second. If doubling the concentration of the species doubles the rate, then the reaction would be first order, and my reaction would be rate equals K times just the concentration of A. These are little tricks that you will learn as we go along to look for. So why do we need rate laws? Well, it allows us to work backwards to infer steps by which the reaction occurred. Remember I said that when we look at a reaction, we're only looking at one reaction. We're not looking at the sequence of the smaller reactions or the rate mechanisms that are occurring behind the scenes. One important thing that you'll need to be able to do is tell me the units of K. The units of K depend on the order of the rate law. So for example, if I have a first order reaction with the form of rate equals K times the concentration of A, I told you initially that the rate has units of moles per liter dot seconds. If I have a first order reaction and the rate is equal to K times the concentration of A, I told you initially that rate has units of moles per liters dot seconds. Equal to K times concentration is always in moles per liter. Concentration is always in moles per liter. So if I multiply both sides, because I'm solving for K, by the inverse, these cancel, and I'm left with K is equal to seconds to the minus 1, or 1 over seconds. If I have a second order reaction, which has the form of rate is equal to K, a concentration of A squared, then I have moles over liters dot seconds equals K. And since this is A squared, I'd have moles squared over liters squared. If I multiply by the inverse, these cancel. This cancels with this, and this cancels with this, and I'm left with units of K equals liters over moles dot seconds. So you need to be able to predict units for K. Okay, let's review a little bit. Determining rate laws. The first step is to determine the form of the rate law, especially its order, as I just showed you to do. This must be determined from experimental data. So looking at the following reaction, dinitrogen pentoxide yielding nitrogen dioxide plus oxygen gas. If you were given this data of concentration versus time, you would graph it. If you graph this data, you would get a graph that looked like this. To find the rate, we have to find the slope at 2 points. So we'd use the tangent method. At our first point, our change in A divided by our change in T would give us 5.5 times 10 to the negative 4. Choosing a second point at 0.4 molar, our change in A over the change in T is equal to negative 2.7 times 10 to the negative 4. Since the rate at twice the concentration is twice as fast, then the rate law must be first order, as I told you a little trick earlier on. So the rate is equal to the change in the concentration of the dinitrogen pentoxide divided by the change in time, which gives us a first order reaction, or the rate is simply equal to the rate constant times the concentration of the dinitrogen pentoxide. The only way to determine the order is to run the experiment. You won't be working with graphing all this data. I'm going to show you how to do it in the calculator. Initially, you'll be doing some of the math by hand, though. So, integrated rate law. Takes the form of a line, y equals mx plus b. Y has the term for the rate, and x has the term for the time. In a zero order, the rate is simply equal to the concentration of A minus KT plus the initial concentration of A. You do not have to memorize these. They're on your reference table. This is for a particular reactant. The change in the concentration of the species, whatever it is that we're studying, has no influence on the rate. If we were to graph this, we'd have the concentration of A over the concentration of T. Looks something like this. So our slope would be equal to the change in A over the change in T, which is equal to negative K. For a first order reaction, first order reactions, it doesn't follow y equals mx plus b exactly. Just want to throw that out there. So you would have the natural log of A is equal to negative KT plus the natural log of the initial concentration. And this would produce, this would be like the ln of A over T. Straight line. In this reaction, the change in the concentration will produce a proportional change in the rate. And in a second order reaction, 1 over the concentration of A is equal to KT plus 1 over A initial. So doubling the concentration of the species, as I said earlier, causes the rate to increase by a factor of 2 squared. Tripling the concentration of the species would cause the rate to increase by a factor of 3 squared.